Hello everybody, this is Dr. Christopher White, and in this presentation we're going to be thinking about the rate of geologic events and geologic time. So this is going to correspond to section 2.6 of your textbook. Now, geology is all about how the Earth's surface and its subsurface change over time, so we're going to be concerned with the rate at which these changes are happening. So we're going to pretty much split events up into two very broad categories: short-term events and long-term events. Now, we need to remember that when we talk about geologic time, we typically work in units of millions of years. And this is because the Earth is 4.54 billion years old. It's extremely old. And so we need to obviously split it up into units of time which are manageable. And blocks of a million years is a reasonable amount of time to use to split up geologic history. Now, in terms of geology itself, another reason why we favour using rates of change over millions of years as a standard is that a lot of geologic processes occur over quite long timescales. So we're talking about events that occur over tens of thousands or hundreds of thousands of years, millions of years, or even billions of years. These are not fast events. And so it makes sense to use millions of years as a unit or a standard unit in geology. Now, when we are talking about short-term events where we have significant change occurring very quickly, well, they tend to be a little less common. So a classic example of that would be something like a meteorite impact. And obviously that can cause very significant change very quickly, but as I'm sure as you know, large meteorite impacts are extremely rare on the surface of the Earth. So there's a very long interval between these events. So the rate at which they occur is very small. So we need to bear that in mind. So a lot of geologic events occur over these very long time scales, and they tend to, when we tend to describe them, we tend to talk about change occurring over units of millions of years, typically as the go-to unit when talking about geology. So the first thing we're going to think about is rate. So rate is a measure of a quantity or frequency typically measured against some other quantity or measure. So the classic example in geology is change over time. So we would describe things like how a mountain range will grow at a set rate, be it centimeters a year or millimeters a year, or centimeters every million years. So our change is typically measured in units such as distance, so centimeters, meters, millimeters, etc. Changes in volume, changes in length, and also the number of events. So we may say, right, over this set time period, how many earthquakes occurred, for instance, how many volcanic eruptions occurred. And obviously time is going to come in a number of units in geology depending on how short or long term the event in question is. So if it's a relatively short event, we might measure it as change over hours or seconds or years. However, a lot of the time in geology, these changes are occurring over longer time periods. So we would measure it in units of thousands of years, millions of years, or billions of years. Now, one of the things that you're going to notice in geology is you're going to see there are lots of abbreviations for these different units of time. So thousands of years can be abbreviated as essentially KYR, or you can also abbreviate it to kiloannum, which essentially is abbreviated to Ka. So you can see that for thousands, millions and billions, we have these different abbreviations depending on what you are trying to describe. So bear that in mind. Typically in geology, you are going to see MA and GA quite a lot. Okay, so megaannum and gigaannum are going to be relatively common units. So essentially a megaannum is representative of a million years. A gigaannum is representative of a billion years. So if you see a number and it's 2.0 GA, that essentially means 2 billion years of time. Now, in terms of the rates at which geologic events occur, they are typically relatively slow. So an average rate for mountain growth is somewhere around 1.5 centimeters per year. There are some places in the world where mountains are growing more quickly than that. There are some places in the world where mountains are growing more slowly than 1.5 centimeters a year. But this is the average rate of height increase when you combine the data from several different mountain ranges. So as you can see, we're essentially looking at an increase in height of 15 millimeters per year. Now, this is actually, quite fast, geologically speaking. If you start to add this up over a time scale of 10 years, for instance, that would mean your mountain range is, of course, increasing by 15 centimeters during that 10-year period. That's quite a substantial change. Now, we don't actually see this change really taking place because the problem is as the mountain is being pushed up, erosion is operating against it to balance it out, and it's removing the rock that's being pushed upwards. So this is why mountains don't keep going up and up and up and up and up, because erosion is constantly trying to cut them down and down and down. Now, in terms of most geologic processes, they are nowhere near as fast as the increase in height of a mountain range. So most geologic processes are slow, and they're going to occur at rates of millions or billions of years. Now, this here is a crude geologic timescale. So we've moved from rate now, and now we're going to think about time. So we can see that the geologic timescale is going to start at about 4.5 billion years ago. So that's 4,500 million years. And it's going to go through to the present day, which is at the top of the timescale here. And you can see that the geologic timescale is split into 4 broad units. At the bottom we have the Precambrian. The Precambrian was then followed by the Paleozoic. That was then followed by the Mesozoic, and then after the Mesozoic came the Cenozoic. So at the moment we are in the Cenozoic. You will notice that there are boundaries between these 4 units. And so we know that the Precambrian started 4.5 billion years ago, and it continued until about 541 million years ago. At that point, we transitioned from the Precambrian and went into the Paleozoic. The Paleozoic went from 541 million years to 252 million years ago, at which point we transitioned into the Mesozoic. The Mesozoic went from 252 million years ago to 66 million years ago, at which point we then transitioned into the Cenozoic, and the Cenozoic is still going on to the present day. So one of the things you're thinking about is, well, hold on a second, this is great, you've split up geologic time, but why have you split it up like this? Well, the 4 main parts of the geologic timescale are based primarily on fossils. So one of the things that a geologist can identify relatively easily in the rock record are fossils. And so what we can do is we can look for when a fossil either appears or disappears, and we can use this to define a boundary. So for instance, a classic example would be something like the dinosaurs. So we know that the dinosaurs existed in the Mesozoic, primarily in 2 periods, the Jurassic and the Cretaceous. Those are periods of geologic time that you've probably heard of. Now, the end of the Mesozoic, so that's 66 million years ago, is of course marked by the KT mass extinction, and this is when a meteorite struck the Earth, essentially causing a nuclear winter, which did very substantial damage to life on the surface of the Earth, the dinosaurs being one of the major species which suffered the worst. Now, in terms of what this means, if we look in the fossil record, when we are looking at rocks from the Mesozoic, we can find dinosaur fossils. As soon as we transition into rocks from the Cenozoic, dinosaur fossils are gone. They're no longer there because the dinosaurs have become extinct. And so this is what we look for in the geologic record. We look for these major changes in life, and we use them to define boundaries in the geologic timescale, because the great thing about fossils is if you select the right fossil, it can be extremely widespread. So you can find it in Europe, you can find it in Asia, you can find it in Africa, you can find it in Australia, for instance. And so you can use that fossil to essentially help date rocks from completely different continents. It's a very powerful tool. So if we look at our geologic timescale, what can we see? Well, rocks from the Precambrian essentially were formed before we had life that had shells and hard parts. So that means shells and skeletons. Now, one of the things I'm sure you know is that when you think about a fossil, what you think about is the shell or the skeleton of the animal. Okay, it's very, very rare that you actually get to the soft body parts of the animal preserved in some way. So what this means is during the Precambrian, life, when it was around, was soft-bodied. And so, of course, this means when that life went and died, the chance of it being successfully fossilized was relatively low, because soft-bodied or soft body parts don't tend to fossilize particularly effectively. Another problem is that for a lot of the Precambrian, life was microscopic. And so you can't obviously see the fossils very easily. You need microscopes to identify them, and even then a lot of the things that are described as microscopic fossils from the Precambrian are somewhat questionable, to say the least. So finding fossils in Precambrian rocks is extremely difficult to nigh on impossible. And so Precambrian rocks are on the whole pretty much fossil free. The only time that we begin to see more complex life being more readily fossilized during the Precambrian is right at the end of the Precambrian, where we have a group of organisms called the Ediacarian fauna beginning to make their appearance. And this is where we start to see complex life beginning to evolve the first stages of shells and skeletons. And so we sometimes find those organisms fossilized because they're starting to develop shells and skeletons, and so they are going to fossilize a little bit more easily. So as we move from the Precambrian into the Paleozoic, we see an explosion in life. So we suddenly see the appearance of important groups like the fish, the plants, the insects, and the reptiles, and the amphibians as well, also all begin to make their appearance during the Paleozoic. So all of a sudden the fossil record explodes with life. So in the Precambrian, rocks are pretty much fossil free. As soon as you move into the Paleozoic, bang, life everywhere in the fossil record. And so you can see we're going to be able to define a very strong boundary there. Below it, no fossils. Above it, loads of fossils. So as we move from the Paleozoic to the Mesozoic, we're again going to see a very substantial change in life. So we're going to see the appearance of groups like the dinosaurs, and we're also going to see the first appearance of flowering plants. So that's the group which we call angiosperms. So we're going to see them beginning to put in their appearance during the Mesozoic. So we're seeing significant changes in the fossil record, and so we can use these to define our boundaries. And then as we transition from the Mesozoic to the Cenozoic, we are of course going to see another very substantial shift in life. So we're going to see the loss of groups like the dinosaurs, and we're going to see the rise of groups such as the mammals and the birds in the Cenozoic fossil record. So this means that as a geologist, if you walk up to a sedimentary rock from somewhere from the Paleozoic, the Mesozoic and the Cenozoic, you can use the fossils in that rock to date what you're looking at. Now, you can't tend to date it, super accurately. You can't say, right, this came from exactly, 260 million years ago. It's not normally quite that good. Typically, you'll have a little bit of a range, and your range might be in the order of somewhere of, 2 or 3 million years. But that's still pretty decent when you consider the Earth as a whole is 4.5 billion years old. So, plus or minus a couple of million years is a pretty accurate dating. Now, when we think about geologic time, we see it drawn up like this, but in reality, geologic time is not equal. So if we look at this geologic timescale at the top here, we can see that the Paleozoic appears to be the largest unit of the four. However, when we actually look at the whole geologic timescale, we can see that the Precambrian is by far and away the biggest unit. So what we've done here is we've actually put the geologic timescale over a calendar, essentially. So we have January 1st here, going all the way through to December 31st here. And so what we're doing is we're splitting the year up based on the geologic timescale. So the Precambrian accounts for approximately 88% of the geologic timescale. So if you're thinking of that over a year, that would be between January the 1st and November the 17th would be part of the Precambrian. Now, the reason that the Precambrian is so big is because it took a very, very long time for life with hard body parts, so shells and skeletons, to evolve. You know, a shell and a skeleton is a very complex thing. Evolution took a while to get there and perfect it. And so this means it took somewhere in the region of about 4 billion years for us to make it to the point where we had life which could be fossilized readily. Now, in terms of the Paleozoic is going to go from the 18th of November through to the 11th of December. So it is a reasonably substantial unit of geologic time. Then, in terms of the Mesozoic, that's from the 12th of December to the 25th of December. And the Cenozoic is from the 26th to the 31st of December. And if you're wondering what about the genus Homo, of which humans are part of, well, we make our appearance in the last few hours. We are a relatively minor part of the whole geologic timescale. So if we look at our geologic timescale, this is a slightly more comprehensive diagram. So we can see we have our 4 basic units, the Precambrian at the bottom, followed by the Paleozoic, followed by the Mesozoic, followed by the Cenozoic. And then you can see that these eras, these larger units, have been split into smaller units, which we call periods. So we have, in terms of periods, we have the Cambrian, the Ordovician, the Silurian, the Devonian, the Mississippian, the Pennsylvanian, the Permian, the Triassic, Jurassic, Cretaceous, Paleogene, Neogene, and Quaternary. And you can see that, of course, we have set boundaries which separate out each of these periods. And once again, these boundaries are based on the fossil record. So as you transition across one of these boundaries, you are going to see certain key fossils either appear or disappear from the rock record. Now, there's a few things that should be pointed out. So you'll notice that the Precambrian doesn't really have any periods associated with it. And once again, this goes back to the lack of fossils. All of these periods are based on fossils. Their first and last appearance of certain key fossils is used to mark the boundaries. When you don't have any fossils in your rock, well, it becomes very difficult to split those rocks up into periods, so you can't really do it. And so this means the periods are only really usable from the Paleozoic onwards. I should also point out that once upon a time the Quaternary was actually, the Cenozoic, I do apologise, was actually split into 2 units, the Tertiary and the Quaternary. And now the problem was that the Tertiary went from 66 million years ago to 2.6 million years ago. So that's a pretty hefty chunk of time. And so it was decided that it would be best to cut the Tertiary in 2, and it was renamed as the Paleogene and the Neogene. One final thing that should be pointed out is that the Pennsylvanian and the Mississippian are also sometimes referred to as the Carboniferous. So the Carboniferous tends to be a term which is used in Europe, whereas the Pennsylvanian and Mississippian tend to be more used in North America. So it's a bit of a regional thing based on differences in geology between Europe and North America. So just bear that in mind. So if I start talking about the Carboniferous at any point, what I'm talking about is a unit of time that covers the Mississippian and the Pennsylvanian combined. Now, once again, we need to remember that most geologic processes are going to occur over a timescale of millions of years. Okay, so always bear this in mind. So most geologic events are going to occur sometimes, between different periods. So when we start forming mountain ranges, the formation of a mountain range might start in one period but finish in another. So, these events are very long, they're very drawn out, and so they can cover multiple periods of geologic time in some instances. Now, when we look at this diagram here, this is a diagram which is summarizing some of the more common rates that we're going to see on the surface of the Earth at the moment. So we can see there are several changes listed in this diagram. So what you'll notice is that a lot of these changes are occurring in units of millimeters a year. So if we look at sea level rise, we can see sea level rise at the moment is anywhere between about 1.8 and 3 millimeters per year. Now, this is relatively fast. Remember, On a human life, on a human scale, 3 millimeters a year may not sound that bad. But do that over 1 million years, and all of a sudden what you're looking at is a very substantial change in sea level. So we need to bear this in mind. The changes that might seem very slow on a human timescale are in fact very, very quick on a geologic timescale. So from a geologic point of view, the sea level rise that we're experiencing at the moment is quite worrying. It's happening very, very fast. And so obviously this means the oceans are eventually going to start encroaching onto the land. And, that's probably not going to be a particularly good thing. So other rates that commonly occur, sediment compaction. So obviously rivers and other processes are constantly depositing sediment. So how quickly is that sediment being compacted? And of course, compaction is very, very important to geologists because it's this compaction of the sediment, it's compression, which is part of the total lithification process, which takes the sediment and turns it into a rock. Well, this is happening at a rate of anywhere between about 0.7 and less than 2.2 millimeters per year. Typically, the higher the rate of sediment deposition, the higher the rate of compaction will be. So the more sediment you're dumping every year, the faster it will be compacted because you're adding more and more weight on top of it quickly. So once again, this is a rate, this is a pretty variable rate, and it is anywhere, between about 0.7 and 2.2 millimeters a year. This is, once again, over 1 million years will actually add up in some instances to the deposition and compaction of quite substantial amounts of sediment. But it's going to depend on your environment. So if we look at the sedimentation rate that we see, sedimentation rates will vary anywhere from about 0 to 50 millimeters per year. So you can have some areas of the Earth where you have very, very high rates of sedimentation, where sediment is being deposited in huge quantities. A classic example of that kind of scenario would be somewhere like the Himalayas. So the Himalayas are an actively growing mountain range, large amounts of erosion taking place, and this is obviously going to produce huge amounts of sediment, which is going to be transported and distributed over the surrounding area. So this means that the areas surrounding the Himalayas are going to have very, very high rates of sedimentation. In contrast, if you were to go out into the deep, deep ocean, so you go out into the middle of the Atlantic and sit on the seafloor, what you would notice is that the rate of sedimentation in that environment is extremely slow. So it would be way less than 1 millimeter a year. In fact, you'd be looking at a rate of sedimentation of maybe around 1 millimeter every 1,000 years. So sedimentation rates are highly variable, so bear that in mind. But once again, it does mean that from a geologic point of view, sediments can be deposited quite quickly or they can be deposited quite slowly. It just depends on the environment that you're looking at. But if you have a very fast rate of deposition, once again, extend it over 1 million years, you can end up depositing some very substantial amounts of sediment during that time period. And then we have the process of isostasy. So isostasy, we've already covered it, but essentially it's what happens when we put weight on the crust. So imagine if I was to put a glacier on top of the crust here, and that glacier was 3 to 4 kilometers thick. So it's a really big layer of ice. Well, what's the weight of that ice going to do? Well, obviously it's going to push down the crust. And what's going to happen when that ice melts and disappears? Well, obviously the crust is going to bounce back up. And so this flexing of the crust as it's loaded and unloaded is referred to as isostasy. And so we can still see it happening now. So during the last ice age, we had substantial ice sheets covering large areas of, for instance, Canada and Scandinavia. And what we're seeing in these areas is that now the ice sheet has retreated, that land is actually bouncing back up. Because remember, when the ice sheet was on top of it, the weight of the ice was pushing it down. As soon as the ice is removed, the ground starts to bounce back upwards once the weight has been lost. And so the rate of isostasy is quite slow. It's between 0 and less than 1 millimeter a year. So it's a very, very gradual process. But once again, spread it out over a 1 million or a 10 million year time frame, and it can actually add up to a very substantial change in the height of the land. So Always bear this in mind. A lot of geologic processes on a human timescale are extremely slow. However, when we extend them out over longer timescales, so millions or tens of million years, it can actually lead to very significant change. So let's look at a few rates down here. Now, we know that the surface of the Earth is split up into regions of rock which we refer to as plates. And these plates are moving around on the surface of the Earth relative to each other. They're constantly in motion. Now, we know that the rate of average plate movement is somewhere in the region of centimetres per year. Now, it's variable depending on where you are in the world. Some plate boundaries will have quite fast rates of movement, some plate boundaries will have quite slow rates of movement. However, if you want to try and visualise how quickly these processes are occurring, let's think about the North Atlantic. Now, it just so happens that the North Atlantic is growing at approximately the same rate as your fingernails grow. So if you look at your fingernail and you keep track of how quickly it's growing, over the same time period, about the same amount of rock will have been added to the floor of the Atlantic Ocean. So just to give you some idea, over long timescales, these relatively small amounts of additional rock can result in quite substantial changes. So going back to the North Atlantic, we know the North Atlantic started to form about 200 million years ago. And over time, it steadily widened until it's the huge body of water that it is now. So the formation of the Atlantic as we look at it at the moment has taken somewhere in the region of about 200 million years. So over a million-year timescale, a 10 million year timescale, a 100 million year timescale, these relatively small rates of change are adding up to substantial movements. Now, in terms of other events such as avalanches and rock slides, well, these can be extremely fast. They can be anywhere in the region of 300 to 500 kilometers an hour. So this would be a geologic process that occurs very, very quickly. In contrast, events like lava flows are highly variable. So when we think about lava flows, we will typically think of documentaries and news reports very often where they show lava flows in places like Hawaii. Now, that particular type of lava is called a mafic lava, and it actually has quite a low viscosity, so it flows very, very easily. So this means the lava flow can move very, very fast. However, that's not the case for all types of lava. There are some other types of lava, which we refer to as felsic lavas, which are very, very high viscosity. They're very sticky. So think of them like cold molasses. And so it's going to take a very, very long time for these lava flows to be able to progress. So the rate at which a lava flow will move is variable, and so we actually wrote the word honey here to kind of demonstrate that a lava flow will have that kind of sticky, highly viscous physical property to it, which means it's not going to move that quickly. But over long geologic periods of time where you have protracted lava flows, you can actually have lava slowly spreading out over quite large areas. And so, areas of the globe where we have substantial amounts of lava building up are areas such as the Siberian traps of Russia or the Deccan traps of India. These are areas where we had prolonged, very, very large volcanic eruptions taking place, and this led to huge areas getting covered in extensive lava flows. And then we have another process such as glacial retreats. This occurs on a rate of millimeters per year. And of course, this goes for both glacial retreats and glacial advances when the glaciers start getting larger. And so what we can see in the geologic record is we can actually get evidence that allows us to, look at, well, under normal conditions, how quickly or slowly would we expect glaciers to retreat? And when we compare it to modern values, what do we see? We see that modern glaciers are actually retreating a little bit faster than we would expect them to. And therefore we can say, right, well, chances are that retreat is probably being accelerated by global warming. So once again, though, when we start adding up this glacial retreat over a million-year time period, it's going to add up to very substantial changes, and that's going to have a very significant impact on the geology of that area. So when we bear in mind that most processes that occur in geology are relatively slow, you'll only get centimeters of change over 1,000-year time periods. we need to remember that when you spread these out over a large timescale, they can actually make very substantial changes. In terms of relatively fast geologic processes that occur in the timescales of meters a second or or centimeters a second, these are relatively rare and tend to be associated with quite violent and short-lived events. The classic example once again being the impact crater. So the final thing that we're going to think about is the rate of geologic change and how it changes over time. Now, in a lot of instances, geologic change is what we refer to as non-linear. This means it is variable, so rates will change over time. Change is not a constant. And so, for instance, if we wanted to give an example of a non-linear change, we can quite clearly see this graph here has this upward trajectory. It has this curved path to it. That is a non-linear rate change. Now, we see this a lot in geology. We see that processes at certain points in Earth history will be operating quite quickly, and the same process at another point in Earth history will be operating at a much slower rate. So a lot of the time, most geologic changes tend to be non-linear. And so a classic example of that would be something like a mountain range. Initially, you'll see the mountain range growing very, very quickly. Then as the mountain range formation starts to slow down, you'll see that rate start to even out. And then on the other side, when the mountain range stops growing, you're going to see it start to be eroded away, and you're going to see the height of that mountain range dropping. And so this is the result of this non-linear change taking place. Now, in terms of geology, linear changes do occur, but a lot of the time they tend to be over shorter time periods. So in a linear change, the rate is consistent over time. So think of an example of a glass of water, and every second you put one drop of water into that glass. Well, every drop of water is going to be the same size, so every time you put a drop in, the water level inside the glass is going to increase by the same amount each time. So the change is going to be constant. Now, in terms of geology, linear rates, as I say, are not particularly common, and they'll often only occur over shorter time periods. So areas of geologic study where we tend to find linear rates are areas such as spreading at mid-ocean ridges. This is where new seafloor is being made. So the classic example is the mid-Atlantic ridge that runs down the middle of the Atlantic. This is a place where two plates are moving away from each other. It's allowing magma to rise up underneath through this gap that opens up, and this magma will then cool and solidify to create new seafloor. Now, on a relatively short time scale, so we're talking a time scale of maybe a few million years, this rate is relatively linear. However, when we look at it over a longer time scale, so tens or hundreds of millions of years, we are going to see that the rate is in fact non-linear. So the North Atlantic is a good example of this. If we look at the rate of new crust being made at the Mid-Atlantic Ridge, if we think about it over a time frame of 500,000 or 2 million years, the rate at which that crust is being made is going to be relatively constant, so it's going to appear linear. However, when we actually look at it over the entire 200 million year lifespan of the North Atlantic, what we're going to see is that the rate at which new crust is being made at the Mid-Atlantic Ridge has in fact changed over time, and so the rate is non-linear. So a lot of linear rates in geology tend to be associated with relatively short-lived events. Okay, everybody, thank you for watching and take care.